Hello, everyone. We're going to be going over the last part of 1.2. We're going to be talking about whether a function is even, odd, or neither. You may remember a little bit about even and odd when we were talking about the trig functions. Cosine was an even function along with secant, and then actually all the other trig functions were odd functions. But we're going to extend that out to not just the trig functions, but to just functions in general. And we'll be using these definitions here of what it means for it to be even and odd. So a function is even if for all values of x, f of negative x is equal to x. One way to think about this is if you plug in a negative value and then the corresponding positive value, you're going to get the same output. So like -2 and +2, if you plug those both into the function, you'll get the same output. And that should be true for all values of x if the function is even. We're going to be using this definition to algebraically demonstrate whether a function is even. Another way that we can kind of look at even is even functions are symmetrical across the y-axis. So they'll have symmetry across the y-axis. An odd function, that's the other one that we're going to be looking at. Odd functions for all values of x, f of negative x is equal to negative f of x. That's a little bit trickier to go. But basically, if we plug in a negative value, we're going to get the opposite of plugging in that positive value. And that's one way to think about it anyway. We'll use these function definitions again to algebraically determine if we have an odd function. Not all functions are going to be even or odd. They could be neither of these. In fact, many, and I would venture to say probably most functions are not even or odd, but it's going to be useful in some cases to know if they are. So odd functions also have a type of symmetry. They're symmetrical through the origin, or some people also say that they have rotational symmetry. So what this means about being through the origin is if we have a point here, then there is going to be a corresponding point through the origin right over here on our graph. That is the same thing as that sort of rotational symmetry. If we rotate it 180 degrees about the origin, we'll find a corresponding point there. We'll take a look at the graphs along with the algebraic approach of determining whether a function is even or odd. So let's go ahead and do our first example here. We're going to try to determine if this function is even, odd, or neither. So I'm going to go ahead and run through testing it for both. So we'll start even. So for an even function, remember the definition is this, that f of negative x is equal to f of x. So we're going to show what those things equal to and simplify them and see if they're the same or not. So f of negative x would be plugging in negative x in place of all of these x's here. So we would get negative x to the third power plus 7 times negative x. That's me simplifying this down right here. And we're going to try to determine whether or not that's going to be equal to the original function f of x. So the original function, no changes made to it. Okay. So obviously there's not much we can do to simplify this right-hand side, but we'll try to simplify the left-hand side down a little bit. So negative x to the third is negative x times negative x times negative x. Multiplying those three negatives together is going to result in a negative, and then we'll end up with x to the third. And then 7 times negative x will turn into negative 7x. There we go. So that's what we can do to simplify that. Now we have our question, are these the same? Are they actually equivalent? And the answer, hopefully, that we're seeing is that they're not. These are not the same thing. I still have x to the third and some similar looking things, but they're not exactly the same. Therefore, this is not an even function. If it were even, they would be exactly identical. So that leaves us to try to see if they are odd. So again, remember that an odd function follows this definition that f of negative x is equivalent to negative f of x. So we've already done this f of negative x, right? We did that same thing here for the even definition. So I'm going to go ahead and copy that down, what we ended up with at the end. Negative x to the third minus 7x. Right? I don't need to do the work twice. I've already done that. I haven't done negative f of x, right? What that means is I'm going to be taking a negative, I'm going to be multiplying the entire function f of x by that negative. So that means to go ahead and distribute this in and to see what happens with this. Let's go ahead and do that. Negative times x cubed will turn into negative x cubed. Negative times positive 7x is going to turn into negative 7x. And now we can see these are the same, right? These actually are the same. This and this, they are the same. So we're dealing with an odd function. So f of x is odd. It is an odd function. So there are some shortcuts we can sort of do with this. We won't necessarily have to test both things every single time. Well, you know, you may find that the first one you test is what is going on, but especially with polynomial functions, actually particular to polynomial functions, the highest power should give you an indication of what it could be. Doesn't mean it will be. This number is odd, therefore I should test to see if this is an odd function. It won't always be odd, but it could be. It won't be even. So anytime we have polynomial functions, you know, x to some power and then descending from there, right? We should be able to kind of use that as a guideline to decide, should we look at this being an even function or an odd function, which is it going to be, and then just make that one test there. So since this was an odd power, we should only test odd. Let's go ahead and take a peek at the graph. So that's what I'm going to do here. I'm going to minimize this real quick. So here's the graph of this thing. It's hard to look at. Let's zoom out. And actually, let's just change the scaling along the y-axis. Let's go from like, I don't know, negative 50 to positive 50. Okay, it's hard to see it. This is quite a large polynomial here, so you can see that this has that rotational symmetry, or that symmetry through the origin. You could imagine if we rotate that graph around 180 degrees, you know, it'd sort of line up with itself. Anyway, let me go ahead and fix this real quick. Let's just zoom in. Alrighty, that should work for everyone. Let's go ahead and turn that one off. We're going to look at these other equations next. So, all right, next example, example number 2. Here we have another polynomial equation. We have f of x is equal to x to the 3rd power. So we're going to try to determine if this is even, odd, or neither. So quick little indication, again, with these polynomial functions, the power can give you an idea of what to test. This is an even number, so I should test to see if this is even. So we're testing to see whether or not this is an even function. Okay, let's run through that again. Remember, the definition of that is that f of negative x is equal to the original function f of x. Simplify this down a little bit. Let's go ahead and figure out what this is equal to. Again, we're replacing the x's with negative x's, negative x to the 2nd power minus 4. So that looks like. Not a lot to do here. Negative x to the 2nd is just negative x times negative x, which turns into positive, negative times negative, x squared minus 4. And is this equal to the original function? Is this equal to f of x? Well, right, it does. It matches exactly the original function. Therefore, this is an even function. So f of x is even. Cool, right? Okay, let's go ahead and take a peek at that graph as well. So let me minimize, go back here. And here is the graph of that equation, y equals x squared minus 4. And we can see it has that symmetry that we're looking for. It is symmetrical across the y-axis. So just by glancing at the graph, we could have probably determined this, you know, in a different manner. Let's go ahead and go back. 3rd example here, we have this equation. This one is not a polynomial function, therefore we can't just automatically assume what we were doing before based on the powers. We're going to have to test, you know, possibly both things. I'm going to start off by testing odd because, well, I happen to know how this problem works out. So let's go ahead and test to see if this is an odd function. Remember, the definition that we're dealing with there is that f of negative x is equal to negative f of x. In this case, we'll have to simplify both of these things down and sort of see what happens. So let's do f of negative x first. Again, that involves replacing all of our x's with negative x's. So it's negative x times the square root of 1 minus negative x squared. Again, when you're plugging this negative x in, it's really important to put it in parentheses, especially when we're dealing with things like powers like this. It's going to make a big difference. So let's go ahead and carry this forward, sort of see what happens. Obviously, this just is negative x times the square root. 1 minus negative x squared being negative x times negative x. So that's going to be 1 minus positive x squared. So 1 minus x squared. Okay, I don't really see much further that I can do to simplify this. So I'm going to go ahead and move over to the other side and simplify down negative f of x. So let's do that. That's negative times the entire function, x root 1 minus x squared. Since this is really just a singular term, it's these two things that are multiplied together, all I'm going to be doing is just sticking a negative in front of that first x. And there we go. Are these equal? Yeah, they look equal. They're exactly the same. Therefore, in this case, f of x is odd, or is an odd function. We'll go ahead and take a look at this graph here in just a moment. Minimize this. Okay, turn that one off. Again, I'll take a peek at this one. Glancing at the graph is a very useful tool here, and it has that rotational symmetry, or that symmetry through the origin that odd functions are supposed to have. So if we click on a couple points, right, these points are symmetrical through the origin there, and then likewise this point is symmetrical at this point here through the origin. So it has that rotational symmetry, or that symmetry through the origin that odd functions are supposed to have. Alrighty, and we're going to do the last one. You may guess what it is based on what I have kind of loaded in Desmos, but that's all right. Let's go ahead and take a look at our final example, determining whether we have an even or odd function, or neither. Again, remember, neither is an option. Polynomial function again. So the exponent here should lead us to know that we should test even, see if this is even. So remember, even is f of negative x equals f of x. We want to see if that's true or not. So let's go ahead and evaluate f of negative x. That's negative x to the second power plus 2 times negative x minus 3. Let's carry that forward. Negative x squared is just x squared. 2 times negative x becomes minus 2x, and then minus 3. So is this equal to the original function f of x? It's not, right? It's pretty close, pretty close. We have x squared, minus 3, but right here, this sign, because of plugging in a negative x, became different. So this function is not even. Now, I do happen to know that it's not really worth our time to test it to be odd, but I am going to go ahead and just carry through that and just show that it is also not odd. So remember, odd is f of negative x equals negative f of x. So we've already simplified f of negative x. Right? We already know what that equals. That's going to equal x squared minus 2x minus 3. And again, we want to know if that is equivalent to negative f of x. So let's simplify what negative f of x would be. That's negative times the entire function f of x. Okay, that's going to cause us to sort of distribute. That's negative x squared minus 2x plus 3. And I think it's easy enough to see that these two are not the same, right? These are not the same. We do get the correct minus here, but distributing it caused these other terms to be different. So this is also not an odd function. Therefore, it's neither. And many functions will be neither. So just because it's not even doesn't mean it's odd, or vice versa. It can also be neither. Many functions will be neither even or odd. And let's quickly glance at the graph of this just to sort of confirm that. right? Remember, even functions are symmetrical across the y-axis. This is not symmetrical across the y-axis. The y-axis is not passing right through the center of this parabola graph, and it's also not rotationally symmetrical or symmetrical through the origin. So it has neither of those symmetries that even and odd functions are supposed to possess. Therefore, kind of easy to conclude that it is neither. All right, see you guys later.